Hello everyone. So today we will be covering some basic physics topics related to heat transfer, gaseous state, kinetic theory of gases, and a little bit part of thermodynamics. These are some related topics and we would be covering these, and with the theory I will also be taking some questions to clear the concepts about how what are their applications and how questions are made from these topics in JEE examination. So first of all, let us see something in gaseous state. So uh, these are some basic things and property of gaseous states that we know. So here are these six property of gases. So what they say, they do have definite shape and volume. They occupy space, unlimited dispensability, high compressibility, low densities with negligible intermolecular forces. Gases exert pressure on the walls. They diffuse rapidly through each other to form homogeneous mixtures. So these were some of the properties that we already know. So let us directly uh, come to the state gas laws, and then we will be seeing the equation of state of a perfect gas or an ideal gas. So here these are some terms: mass, volume, pressure, temperature, that we already know. Temperature is represented in degree Celsius, degree Fahrenheit, and basically Kelvin also. So let us see some laws. So here we have this Gay-Lussac's law or Emanton's law. So what does Gay-Lussac's law says? If it states that at constant volume, the pressure of a given mass of a gas is directly proportional to its absolute temperature. So basically, according to this law, pressure is directly proportional to temperature when volume is constant. So we write it as P is equal to KT, where K is some constant. So P by T is constant. So in Gay-Lussac's law, we can directly write it as P1 by T1 is equal to P2 by T2, which is equal to constant. So let us see the next law. The next law is Boyle's law. What Boyle's law says is if temperature is constant, then pressure into volume, the term pressure into volume also remains constant. That is P1 V1 is equal to P2 V2. So how these laws comes, these laws comes by this single equation, that is PV is equal to nRT. This is the ideal gas equation, or we can say it as state equation of a perfect gas. So let us see. All the laws are derived from this only. Suppose in Gay-Lussac's law, temperature is constant. So we say, in Gay-Lussac's law, volume is constant. So we say the ratio of P upon T is constant because N is the moles of the gases that remains constant. R is a constant. R is 8.314 joule, and volume is directly we have taken it constant. So we can say that P by T is constant. So if we remember this single equation, that is PV is equal to nRT, the state equation of a perfect or an ideal gas, then we can derive all the three laws. So just remember, Gay-Lussac's law say volume is constant, Boyle's law say temperature remains constant. So for Boyle's law, P1 V1 is equal to P2 V2, and for Charles' law say when pressure remains constant. So when pressure remains constant, are the ratio of volume and temperature remains constant over the entire container. So at that time, basically not a container, um, for a container with a piston, because at that time pressure remains constant. So the piston would be moving up and down in the container to keep the pressure constant, and the volume would be changing. Volume and temperature would be changing. Okay, so now let us see some applications. Okay, so here for 1 mole of gas we directly write PV is equal to nRT, but generally we do not directly always take 1 mole of gas. So let us say the significance of R. So R is PV by NT, pressure into volume upon moles into temperature. So R can be, numerical value of R is numerical value of R is given to us by some assumptions that we have already taken, by some lemmas and by some postulates. We know the value of R, and this is to be learned, which would be used in the questions earlier. Afterwards, R is equal to 8 to 1 when pressure is in liter, temperature and volume is when pressure is in atmosphere and volume is in liters. When pressure when pressure is generally in its SI units and volume is also in its SI units, then R is 8.314 joule Kelvin inverse mole inverse. So basically these two values we have to learn. R is equal to 0.0821 liter ATM, and the most used form R is equal to 8.314. Okay, now let us see Dalton's law of partial pressure. Now what does Dalton's law of partial pressure says? Dalton's law of partial pressure says that according to this law, when two or more than two chemically inert gases are kept in a closed container, suppose a closed container has helium and it also has neon. So why I have taken helium and neon, and why not I have taken H2 gas and O2 gas? Because we need to take two gases that are inert that do not each other. So I am taking helium and neon. So suppose helium has a pressure of 10 atm and neon has a pressure of 2 atm. So when these two gases are present in a container, so the total pressure of the container would be the sum of the pressure of these two gases. Similarly, if I say in the container I have n gases and in n different inert gases that do not react with each other, so for these, this inert term, this inert gases term is very much important, because if the gases start reacting, then this law fails. So for this law is only true for inert gases. So suppose there are n gases in a container, so the total pressure of the container would be the summation of pressure of all the would be the pressure of all the gases that are present in the container. So we write the pressure as P1 plus P2 up to Pn. Now suppose we have that container. Suppose that is a rigid closed container. Since the container is a rigid closed container, the volume is fixed. So we can write the total pressure as P, volume as V, which is now equal to moles of the container. Now suppose there are two gases, helium and neon. Helium has N1, neon has N2 moles. So gas 1 or gas 2, let us see. So N1 plus N2, that is the moles, and R, and the temperature is the same, that is the temperature of the container. We can write this equation. For gas A and B, we can further write gas A and B, we can also write their partial equations of state, that is PAV is equal to N1 RT, and then we can also write PB V is equal to N2 RT. On adding these, we get PA plus PBV is equal to N1 plus N2 RT. Therefore, we get P is equal to PA plus PB after comparison. So this proves our Dalton's law of partial pressure. Now let us quickly move to the applications that we would be requiring. Now, now this is one of the application of the uh, Dalton's law of partial pressure. This is basically Graham's law of diffusion. What does Graham's law of diffusion says? The rate of diffusion of gas 1 to the rate of diffusion of gas 2 is directly proportional to their partial pressures and inversely proportional to the root of the diameter, root of the root of the densities of the two gases. So basically, we say the rate of diffusion of a gas is directly proportional to the partial pressure of the gas and inversely proportional to the root of the density of the gas. So suppose we say R is directly proportional to P and R is proportional to 1 by root D. So we get R is equal to K times P by root D. Now we don't know the value of K. So what we will be doing is we will be using this application in comparing the diffusion of two different gases. So we will divide R R1 by R2. So we had R1 is equal to K P1 by root T1 and we had R2 is equal to K P2 by root D2. So what we will do is we will divide them R1 we will divide R1 by R2. So we will get P1 by P2 root multiply by root D2 by root T1. Okay. Now suppose if the pressure is constant, in case of Charles law, R1 by R2 would be root D2 by D1. Suppose we take um, that pressure is not constant, but the densities of the two gases is same. Then we will get R1 by R2 is equal to P1 by P2. So this can be used in a different ways. Now, what is vapor density? Vapor density is basically molecular mass divided by 2. Vapor density is basically molecular mass of the gas divided by molecular mass of H2. So here this 2 came because the molecular mass of H2 gas, hydrogen gas is 2. So basically this 2 is because of that. So by this density D1, we will replace it by molecular mass of the gas divided by 2, and so we replace this d2 by m2 by 2 and d1 by m1 d1 by m1 by 2. We replace d1 with m1 by 2, so the 2 factor gets cancelled and we get r1 by r2 is equal to root m2 by m1. So where m1 and m2 are the molecular masses of the two gases. So this was the basic thing, that was for Graham's law of diffusion. Just take a quick look at these three formulas. Okay, cool. So now let us move to the point kinetic theory of gases. So what does kinetic theory of gases says? Kinetic theory of gases is basically some assumptions given by 3 to 4 scientists, and sometimes these assumptions are directly asked in JEE-Mains in the assertion and reasoning questions. So we will have a look at these as we will have a look at these assumptions, and I will say you to I would be saying you to learn these assumptions so that you can recall them while you are doing questions in JEE. So the first assumption says that all the gases are made up of molecules moving randomly in all direction. So yeah, it is true. It is the most basic assumption. The volume of the individual molecule is negligible as compared to the total volume of the gas. So see, the volume of a single molecule is represented by the variable B. We say the volume of a single molecule is B. So generally, by this assumption, we say B is nearly equal to 0 or B is equal to 0. So by this assumption, we say the volume of individual molecule is 0. Second, pressure exerted by gas is due to the collision of gas molecules with the wall of the container. So pressure is equal to number of collisions per unit time per unit area by the molecules on the walls of the container. We say the pressure is directly proportional to the number of molecules, number of collisions per unit time per unit area. That is basically force upon unit area. So we say the pressure is due to the collisions of the molecules with the walls of the container. All collisions between two molecules in a molecule and a wall are perfectly elastic. So the coefficient of restitution, that is E, is equal to 1 for the molecules when they collide with each other. So this is a basic thing uh, when we talk of collisions between two particles. All molecules obey Newton's laws of motion. This assumption says that the collisions are same as what we have read in our 11th class free body dynamics. They follow Newton's laws of motions for that equal equal and opposite forces are present in a collision. So, and the Newton's first law of motion, Newton's second law, and the third law. What the sixth point says is gas molecules neither attract nor repel each other. This says that if a molecule is going in direction x and there is another molecule which is going in direction y, so they do not interact with each other. They will not be having any interaction, and not be they will not be applying any force on each other. So this is again another assumption. Now we have another assumption as kinetic energy of gas molecules depend upon absolute temperature. So kinetic energy is proportional to absolute temperature. We will further see kinetic energy is equal to 3 by 2 kT, and kinetic energy is equal to um, um, nRT, where n would be degrees of freedom. So we will see how kinetic energy depends on x by 2 kT, how kinetic energy depends for different degrees of freedoms of gas, where x is the degree of freedom of the gas. So um, here we see, here it is written, and further we will see what is the formula for kinetic energy. The force of gravity has no effect on the speed of gas molecules. It's very much true, because it can also be seen as the gas molecules have negligible mass, and since they have negligible mass, so the force of gravity has no effect on them. So it is just an assumption. Like there was an assumption that the volume of the gas molecules is zero. Actually, this is not zero. It is very less, but it is present there. But in this assumptions, we will always assume that what these assumptions says are true. Now see, here comes the kinetic energy. Here comes the calculation of kinetic energy. Basically, how kinetic energy and temperature are dependent on each other. Direct questions come on this concept in JEE, and questions come in the type of integers and also like in single characters questions. So first of all, let us let us see the postulates. According to postulates of kinetic gas equation, PV is equal to, what is the postulate of kinetic gas equation? PV is equal to nRT. So pressure into volume is equal to moles nRT. So PV is equal to nRT, and here we are substituting it by number of molecules present in the gas amount root mean square. So here we are like using this equation, but we directly do not need this. Okay, let us see this diagram. Here there is a molecule. So before collision, this molecule is moving like this. After collision, since it follows Newton's laws of motion, so and it collides elastically with the wall, it will impart an velocity in the opposite direction. from which it was coming, and the magnitude of the velocity will remain same. So it continuously performs this motion, assuming that there is no other particle colliding with it while it is performing this motion. Okay. So for 1 mole of gas, PV is equal to RT, and let us also uh, for an instant learn this postulate of kinetic gas equation, which says pressure into volume is 1 by 3 times mn v bar square, where v is the root mean square speed. Root mean square speed. Okay. Now we know 1 by 3 mn v square is equal to RT, because PV is equal to RT, and kinetic energy is half mv square. So we multiply by 2 and divide by 2, and we replace half mv square by kinetic energy. So 2 by 3 kinetic energy is equal to RT. And since uh, kinetic energy uh, n, let us divide this thing by n and multiply it by n. So let us divide both side by we know kinetic energy is equal to half mv square. Divide both side by capital N. So we get average kinetic energy per mole. So kinetic energy per mole is equal to half mnv square. So 2 by 3 Ke is equal to RT. Kinetic energy is 3 by 2 RT. Kinetic energy per mole per average kinetic, or we can say average kinetic energy per mole. Now we have this 3 by 2 RT. After after a certain time, we will know that kinetic energy is x by 2 RT, where x is the degree of freedom of the gas. Here we are assuming the degree of freedom of gas is 3. Okay. Now, we know that this R can be replaced by Boltzmann constant. That is K is equal to R by N. So you get the absolute kinetic energy per molecule, not per mole. We get the kinetic energy per molecule as 3 by 2 kT. Here the N goes in. Here there was an N in this multiplication that goes into denominator, and R by N is converted to K. So we get kinetic energy is equal to 3 kT by 2. So this is kinetic energy per molecule. So you should know whenever it is asking kinetic energy per mole, then you will write 3 by 2 RT. And whenever it is asking kinetic energy per molecule, you will use 3 by 2 KT. Okay. Now let us see what is root mean square velocity. Root mean square velocity is basically is just an assumption. Suppose an container has n particles. So, and all of those n particles have velocities v1, v2, v3, v4 up to vn. So what would be the root mean square velocity? Root mean square velocity would be root of v1 square plus v2 square up to vn square divided by n. So first we would be squaring the velocities, then we would be taking the mean, and then we have the root. So this is basically root mean square velocity. What does root mean square velocity suggest us? Basically, this is a sample space. This shows this was used in the formulation of basic postulates of kinetic theory of gases. So this doesn't have much significance, but it has a little theoretical importance while forming the postulate. Let's see. Root mean square velocity, which is taken as c, is equal to root 3 pv by m. We directly have to learn this formula because this formula would be coming in exam. We would be using it. We can derive it, but generally this is not feasible to put much time into deriving these formulas. So we have this formula, and then we replace pv by nrt. So we get root 3 rt by m, since there is only 1 mole. Also, we replace m, we divide here by volume, and here also we divide by volume. So we get RT by V as P. So we get root 3P by D, where D is the density. So basically you have to learn this formula, root 3 RT by M, and all these two formulas can also be derived. And what is average speed? Average speed has the formula root 8 RT by pi M. Average speed is 0.9213 times RMS speed. RMS speed is 1.0185 times the average speed. So you should know this relation. Most probable speed, that is root 2 RT by M. In JEE 2021, this question came: what is which is the which speed is the fastest, or like directly this ratio was asked in the questions, that uh, where we would where we were required to tell that which is the greatest speed among most probable speed, average speed, and RMS speed. So you should know that RMS speed is the fastest, is the greatest speed among the all, and most probable speed is the lowest speed. So this is the ratio you should just keep in mind. Okay, now let us see mean free path. Now, what is formula for mean free path? First of all, we should be clear with the definition of mean free path. What does mean free path says? Mean free path says mean free path says is that the distance the distance a particle covers between two successive collisions is known as mean free path. Similarly, what is mean free time? Mean free time is the time that a particle invests between two successive collisions is known as mean free time. So first of all, let us see the formula for mean free path. Lambda, which is mean free path, is written as 1 by root 2 pi sigma square times RT by PV. Okay. Now here what is now here RT by PV. P is the pressure, V is volume, T is temperature, and sigma sigma is basically sigma is a Stephen's constant, which we know. Now, as size of gas molecules increases, mean free path decreases. As V increases, mean free path decreases. At the room temperature and at the pressure 1 atm, the order of mean free path is of 10 to the power minus 5 centimeter. So this you need not to remember, because this is not directly asked, but you should remember this formula. Lambda is equal to 1 by root 2 pi sigma square RT by PV. Okay. Now let us see van der Waals equation. Now what does van der Waals equation says? Van der Waals equation is basically a modification in the state equation of perfect gas. That is, van der Waals equation is just an modification of ideal gas equation. So van der Waals equation says is that uh, the molecules, the molecules that are present, the gaseous molecules that are present in a container occupy some volume. It is not true that they have zero volume. They occupy some volume. And as I said earlier, if a gas particle has a volume which is equal to B, then n gas particles will have volume in B. So we say the volume of the container is actually not V, it is actually V minus NB, which is written here. That is, V ideal is equal to V minus NB. Similarly, we have a ideal pressure which is equal to uh, the pressure P is actually not the pressure what we think the gas molecules apply on the wall. The gas molecules apply force on each other. So if a gas molecule is going to hit a wall of a container, there would be another gas molecules that is pulling it from behind. So basically that pressure would be P minus. So there would be a reduced pressure on the container of the wall, and we will get the pressure as P minus n square A by V square. So the ideal gas equation though is modified, and we get the van der Waals equation as P minus n square A by V square into V minus NV is equal to nRT. Okay, so this is a basic equation that they directly generally ask uh, this the dimensions of this quantity B. So B's dimensions is basically volumes dimension L cube mole inverse. So this is just a basic thing. This can be learned. A's dimension, they will ask you A's dimension. So basically A's dimension can be would be dimension of pressure into dimension of volume square upon dimension of mole square. So this should be learned. Here are some limitation of van der Waals gas equation. Let us take a look at them. It could not explain the quantitative aspect of derivation so satisfactorily as it could explain the qualitatively aspect of deviations. The value of A and B were also found to vary with P and T. Okay, the numerical value of Vc was not equal to 3B as derived by van der Waals equation. Vc is basically critical temperature, critical volume that we will see here. Now let us see critical temperature. The temperature above which gas cannot be liquefied whether pressure is applied is called critical temperature. Suppose there is a gas, let's say hydrogen H2. So a gas liquefies at low temperature. Now suppose we put the temperature as 80 degrees Celsius. A gas is compressed when we a gas is liquefied only when either we compress the gas or we reduce the temperature. Now suppose I have put the temperature as 80 degrees Celsius and I start compressing H2 gas. If I start compressing it, ideally after some time I will see some liquid drops in the container. So basically I will see some liquid drops in the container, and I will know that at this temperature the gas is liquefying. But suppose I raise the temperature from 80 degrees Celsius to 100 degrees Celsius. At that point also, I see some drops of liquid as I compress the hydrogen. I raise it to 110 degrees Celsius. At that point, I only see one drop of liquid of hydrogen gas. And at 111 degrees Celsius, suppose I am just taking a random value. Suppose at 111 degrees Celsius, now with at how many extent do I compress the gas, there would be no liquefaction of the gas. I will not see any liquid drop of gas at that temperature, irrespective of how much pressure I apply on the irrespective of how much pressure I apply on the gas. So that is basically critical temperature. Like here the critical temperature was 110 degrees Celsius. Like above 110 degrees Celsius, the gas would not be liquefied whatever pressure is applied. So critical temperature is 8A upon 27 RP. So this should be learned. This can be derived, but this is generally this you have to generally learn this. Okay. Similarly, the minimum pressure required to liquefy a gas at its critical temperature is called critical pressure. So this is the same case as we talked of critical temperature. Here we have critical pressure. Like at its critical pressure, the minimum pressure that we will have to put some minimum amount of pressure. Like we will have to put 10 atm, then only the gas will liquefy. If we will put some pressure less than 10 atm, like 5 atms, then the gas will not liquefy at its critical temperature. So that pressure is called critical pressure, and its value is A upon 27 p square. You will have to learn this. Now, what is critical volume? The volume occupied by 1 mole of a gas at the critical temperature and critical pressure. You have to learn them in this order: critical temperature, critical pressure, and critical volume. So, what volume does the 1 mole of gas occupies at its critical temperature and its critical pressure is called critical volume. So, critical volume is basically 3B, and this is also B. This should also be learned. Now, there is also one more famous question that is constantly being asked in JEE examinations is the ratio of PV and R, the ratio of PV divided by RT. So they ask what we will get if we multiply critical pressure and volume divided by critical temperature. So if we compute PV by RT, we get we'll multiply these two, we get 3AB by 27 p square divided by 8A by 27 RP. So we get 3 by 8. So if we want to know this ratio PV by RT, if we want to know the ratio of PV to RT, so we get the ratio PV is to RT as 3 is to 8. So this should be remembered. Okay. Now, liquefaction of gases. On increasing the pressure, gas can be easily liquefied. I have like directly taught you the theory of liquefaction of gases. Let us quickly read these 3 points. On increasing the pressure, gas can be easily liquefied because intermolecular interaction between gases molecule increases. On decreasing the temperature, kinetic energy of gaseous molecule decreases. That's why gas can be easily liquefied. The third point says temperature of gas must be lower than the critical temperature. These were the points that we discussed earlier also. Now we have seen some assumption of kinetic theory of gases. Let us let us cover a topic. It says work done in isothermal process. Okay, so here I have made the short notes for work done and work done whenever a gas is compressed. So for isothermal process, that is when temperature remains when for isothermal, when temperature remains constant. So at that time we know the formula of work done is integral PdV from V1 to V2. So basically we write it as PV is equal to nRT. nRT is here replaced by mu. Just just assume it as n. So it is like nRT by V dV. So since T temperature is constant, we get T outside, and integration of 1 by V dV. Integration of 1 by V dV is log V. So we get log base E V. So whenever we integrate it and we have the limits present, so we will put the limits log V final minus log V initial, which can be which can be written as log of complete log of V final by V initial. Now, log base E can be converted to log base 10 as 2.303 nRT log 10 V final by V initial. This was very basic. Let us look at work done in adiabatic process. So for a work done in adiabatic process, work done is integral P dV V initial to V final. So for adiabatic process, we know PV to the power gamma is constant. So we write it as KV K upon V by V to the power gamma. So K is written here same exactly. And 1 by v to the power gamma, uh, its integration would be v 1 by 1 upon 1 minus gamma upon 1 into 1 upon v gamma minus 1. So this is again a basic thing. You get this formula. So basically you will have to learn these formula and it would be an easy task for you. So work done in an adiabatic process is P1 V1 minus P2 V2 upon gamma minus 1, and in terms of temperature it comes out to be nr T2 minus T1 upon gamma minus 1. Sorry, nr T1 minus T2 upon gamma minus 1. Now let us see comparison between isothermal and adiabatic processes. So whenever there is compression, if a gas is compressed isothermally and adiabatically from V initial to V final, then from the slope of the graph, it is clear that graph 1 represents adiabatic process, whereas graph 2 represents isothermal process. So they are talking of basically a graph. For adiabatic, the graph is much steeper, and for isothermal, the graph is less steep. So basically work done is area under the PV graph. So since the adiabatic graph is steep between 2 points, so it will cover more area. Since it is covering more area, the work done for adiabatic would be greater than work done for isothermal. So this is basically uh, a normal thing that we can observe by the graphs. Now we may see isobaric process. So for isobaric process, the work done is P dV. Since pressure is constant, pressure comes outside, so we get P V2 minus V1. It was a very basic thing. Law of equipartition of energy. Now, what does this law say? For any system in thermal equilibrium, the total energy is equally distributed among its various degree of freedom, and the energy associated with each molecule of the system per degree of the freedom is 1 by 2 kT. So suppose if a system has x degree of freedoms, the total energy of the system would be x by 2 kT. What it basically says is the total energy is equally distributed among its various degree of freedom, and the energy associated with each molecule of the system per degree of freedom of the system is 1 by 2 kT. Okay, so this was simple. Now let us quickly see some questions on law of equipartition of energy. So energy of all. So let us see this question and then I will be solving this question. Okay. So energy of all molecules of a monoatomic gas having a volume V and pressure P is 3 by 2 PV. The total translation energy of all molecules of a diatomic gas as the same volume and pressure is. Okay. So energy of 1 mole of a gas is x by 2 RT, as we know, which is equal to x by 2 PV. Now, for monoatomic or diatomic, both gases possess equal degree of freedom for translation motion, and that is equal to 3, which is in 3 different XYZ direction. So energy is equal to 3 by 2 PV. So basically, this was the only answer. Although total energy will be different. For monoatomic gas, we have total uh, for monatomic gas, we only have 3 degrees of freedom. But for diatomic gas, we have 5 degrees of freedom. So the answer could be for the total energy would be different. But since they have asked us the total translational kinetic energy of all molecules, so our answer would be 3 by 2 PV. Okay. Now let us see degree of freedom. The term degree of freedom of a system refers to the possible independent motions of a system. Now just see this diagram. What this diagram says is, suppose there is a monatomic gas here. So the particles would be so there would be independent particles here. There is an independent particle present here. So that can possibly go in these three different directions, x, y, z. So for translational kinetic energy, for translation motion, it have three independent directions. So uh, the we say the translational degree of freedom is 3. Now suppose uh, the rotational degree of freedom for a monoatomic gas is 0, because basically this is a monoatomic. So around so there would be uh, there would be there would be no way in which it can rotate and show its rotation. Now diatomic gas. For diatomic gas, similarly there are 3 translational degree of freedom and 2 rotational degree of freedom. So a total of 5 degree of freedoms. How there are total of 5 degree of freedoms? Because the diatomic gas can rotate on an axis of x, on an axis of y, and we are supposing it is placed over axis of uh, z. So it can only rotate over axis of x and axis of y when it is placed along axis of z. So it has 5 degree of freedom. Similarly, triatomic gas can have 6 or 7 degrees of freedom, depending upon sorry 6 or 5 degrees of freedom depending upon what type of triatomic gas it is. If it is non-linear, then there would be 6 degree of freedom. If it is linear, then there would be 5 degrees of freedom. Now let us take a quick look at specific heat or specific heat capacity. So gram specific heat is denoted as delta Q by m delta T, where delta Q is the heat transfer and delta T is the change in temperature. Delta Q is change in heat divided by mass into change in temperature. Molar specific heat is denoted as Q by mu delta T, and its units are calorie per mole degree Celsius, calorie per mole into Kelvin, or joule per mole per Kelvin. So it depends what units of temperature we use. We can also see the definitions of gram specific heat. Gram specific heat says, gram specific heat of a substance may be defined as the amount of heat required to raise the temperature of 1 unit mass of the substance by 1 unit degree. Suppose there is a substance, suppose there is a 1 gram substance. Suppose is a stone which is of 1 gram. So to raise the temperature of 1 gram of stone by 1 degree Celsius, the heat we require, that heat is known as gram specific heat, and we denote it by C. So basically C is equal to heat delta Q, which is heat required to raise the temperature of that substance by that 1 gram substance, that is m, mass of that substance, unit mass substance by 1 degree Celsius, by unit degree Celsius. What is molar specific heat? So remember, molar specific heat is heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. So by this definition only you can derive this formula. You can know this formula. C, capital C, is basically heat Q required for unit change in temperature for unit mole. So Q divided by into temperature. Okay. Specific heats of gases. Let us discuss some few cases that are present here. If the gas is compressed suddenly and no heat is supplied from outside, so since no heat was supplied and the gas was compressed suddenly, the obviously the temperature of the gas will raise, and we will see that delta Q is zero. So specific heat would be zero. If the gas is heated and allowed to expand at such a rate that rise in temperature due to heat supplied is exactly equal to fall in temperature due to expansion of the gas. That is, uh, this is talking of the process that take infinite time. So for this, there would be no change in temperature. This is talking of the ideal process. So there would be no change in temperature. So delta to T would be equal to zero. So we get C is equal to infinite. Now suppose if the gas were to expand very fast, fall of temperature gas due to expansion would be greater than rise in temperature. So due to heat supplied. So we are supplying some heat. Delta Q is positive, but there would be a fall in temperature. So okay, so in the fourth case, we have the specific heat of the gas as a negative quantity. So according to the values given in the question, we can get the value of the specific heat of gases. Okay, we have already seen these cases, and here it is mean free path. We have seen the formula for mean free path earlier. That is 1 by root 2 pi sigma square PV by RT. So here basically this is the same formula, that is lambda is equal to 1 by root 2 pi sigma square, where sigma was the density of the gas. Okay, and here written some average speed, and there are two problems. Let us see this problem number 77 in a quick way. The mean free path of nitrogen molecules at a pressure 1 atm and temperature 0 degrees Celsius is 0.8 into 10 to the power minus 7. If number of density of molecules is 2.7 into 10 to the power 5, then the molecular diameter is. So they have given us the density. So we will directly use the formula lambda is equal to 1 by root 2 pi n d square. So this formula is used. So n is the here lambda is given to us, and they have asked us this molecular diameter, and we know n is 2.7 into 10 to the power 25 per meter cube. So we substitute in here, and we also substitute lambda here, and finally we get d from this equation. So d is 3.2 Armstrong. So this type of questions can be expected in examination. Please kindly also see this question and attempt this problem number 76. It is a very basic question of mean free path.